Let's have now Roberto Serra from University Federal of ABC. ABC.
Okay, thank you. I'm from this university here. ABC means, for who not knows, means a region in São Paulo metropolitan area. So it's funny, but it means 3 cities in the metropolitan area. So we're going to talk about some experiments where we can we start to play a little bit with these quantum features in a quantum engine. In particular, this is the cartoon of this of the kind of the engine that I will show. We use nuclear spins as our work substance, and then at the beginning, I will start to introducing to you what is this kind of implementation and how to characterize reversibility in this kind of engines. And then I will show one possible way to control entropy production and the reversibility in this engine, taking a shortcut from the adiabatic evolution. And in the end, I will discuss how to use coherence, that in general is an extra source of entropy production, to also increase the efficiency and the power that we can extract from that engine. So I will take the advantage of all the introduction that we have in this morning about NMR system given by Alexandre, and also all the motivation about entropy production and etc. that we have in this conference. Then I will jump directly to the results. So these are the people that take part in this kind of research. So this is our local team in São Paulo. This is the team at CBPF in Rio de Janeiro, and there is also this guy in Waterloo, and there are also many other collaborators in other staffs that helped us to develop some technique or some method that we're still using in this kind of experiments. So I will just comment very, very, very short the kind of system that we have. So we have a kind of a sample, which is a molecule diluted in a solvent. This is very diluted. I have just 1% of the molecule that I want to study, so I can neglect any interaction between different molecules. And we can, when we put that sample inside of a Rouge magnetic field, generated by a superconducting coil. In our case, it's about 12 Teslas. So depending on the kind of the isotope that we have different resonance frequencies. In our case, the hydrogen, for example, is about 500 megahertz resonance frequency. So I can choose different huge frequency fields in order to manipulate the nuclear spins of that system. This is an illustration with the chloroform molecule, for example. Here I have a 2-qubit system, and the chlorine works as an environment in this case. So when we perform one experiment in that system, we have the data contain the average over a mesoscopic number of particles. So we have in our samples, we have typically 10 to 17 molecules. Okay, so we can, depending on the kind of the molecule, we have different types of Hamiltonian that describes the effective interaction between the nuclear spins. We have, for this chloroform molecule, we have something similar to the Ising Hamiltonian, and we can switch on and switch off these huge frequency fields in the transverse direction. So we will call the direction where this Rouge magnetic field of 12 Teslas is point as the Z direction, and we can switch on and switch off these fields in the transverse direction in order to control the initial state of the system, and we can also control the dynamics of the system using this part of the Hamiltonian. Typically, in this system, we have two kinds of decoherence effects. One effect is associated to energy damping, and the other effect is associated to a dephasing. It takes a few seconds to happen, and then we can, for example, perform a rotation pi/2 in 10 to minus 6 seconds. So we can do a lot of things inside of this decoherence time. As Alexandre Arad commented, combining free evolutions plus rotations plus gradient fields, we can prepare any initial state that we want for this spin system. And we can prepare, for example, a thermal state in one of the systems, and we can prepare the other system in the ground state, or we can prepare both systems at the thermal state, but this is not the thermal state in equilibrium with the environment. The experiment is performed at room temperature, but we have this spin temperature. This thermal state, this pseudo-thermal state, will last for time smaller than the decoherence time. But we can do a lot of experiments, test, proof of principle experiments in that system. So we play a lot with this kind of dynamics in this kind of experiments. So we can increase and decrease the intensity of this external field in order to open and close the energy gap of the spin system, like expansion and compression in a thermodynamic cycle. We usually do it also changing the phase of the field. So we produce effectively a Hamiltonian like this one that does not commute in different times, and we use to do it in a linear way, but we can also choose another forms for this evolution. These are the typical values that we use to vary the gap. This is in frequency, so we just need to multiply by the Planck constant to get the energy of the open and the closed gap. When we do this kind of evolution, if we do it faster than the adiabatic limits, we will produce transitions between the ground state, the excited, and so on, and then we can produce entropy. So we can use these dynamics together with some thermalization to implement a cycle. We can implement a fridge or engine. This is the engine implementation. So the idea is to start with our working substance, which is a two-level system, many copies of this two-level system, the nuclear spin. And then we increase the gap, and then we let the system thermalize with the hot source, and then we decrease the gap again. We do it in the following way. The reservoir, in that case, is this radio frequency field. So this is the way that we produce this effective thermalization. And then at some point, for example, if we use this chloroform molecule as our working system, we use the carbon as the working substance and the hydrogen as an auxiliary, like a thermal bus. We have to thermalize the system with the hot reservoir at some point in the middle of the cycle, right? So if you let the system thermalize naturally with this field, it takes a lot of time. So in order to produce this finite time engine, we proceed in the following way. We prepare the cold state here, the hot state here, then we use this guy to carry the hot state at the right point to get the thermalization, and then we perform a kind of an algorithm thermalization. After this evolution, the state here is the thermal state of the hot reservoir. We perform a full thermalization in that case, but we can also perform an incomplete thermalization if you want, with just a small modification of this. These are free evolutions, and these cycles represent rotations. So changing a little bit this algorithm, we can also produce a not complete thermalization if you want. But if you can also say, okay, 1 qubit is not a true reservoir, right? It's not a macroscopic reservoir. When we produce what plays the role of a hot reservoir in an internal combustion engine, we use less than 1 milliliter of fuel mixed. Actually, it's about 10 to minus in the modern engines, estimated, getting some data from some companies. It's about 10 to minus 3 milliliters per cycle in each piston. If you consider the molar volume of the fuel, you can see that there are less than the Avogadro number of particles in that fuel that we spread in the cylinder in order to produce the hot reservoir. So even in this classical engine, we don't have a macroscopic reservoir in that sense. So here the reservoir is this classical field, but we use this just to transport the heat to the right place in the cycle. Okay, and this gap expansion, this gap compression is what I presented to you before. And if you compute, as we are dealing with a two-level system, it is easy to compute work and heat in this case in terms of this transition probability. We can solve this numerically because the Hamiltonian does not commute in different times, right? And this is this chi could be a parameter to analyze this cycle. So imposing that I want to extract work from this finite time implementation of an engine. So again, I'm doing this dynamic in a non-adiabatic way. I'm compressing and expanding the gap very fast. And we end up with these conditions. So this is the usual classical condition for the auto cycle. And this condition here is due to the fact that the Hamiltonian does not commute in different times. So we have an upper bound given some temperature. Beta 1 and beta 2 are the inverse temperature of the hot and cold states. And Ni 1 and Ni 2 are the gaps, the open and the closed gap. And here we have a bound for the transition probability to get the engine working as an engine. So as we produce this entropy, due to the transitions between the eigenstates of the city, of the system. So we have, we have to, given a rate for this compression and evolution process, we will get some transition probability, and this transition probability will fix the relation between the temperatures of the hot and cold environment in order to get this engine working as an engine. Okay, we can write the efficiency of the engine in terms of this transition probability, then we can see this kind of condition arriving. And as also Gabriel commented in his talk before, we can write the efficiency of the engine in terms of the auto efficiency, of the Carnot efficiency, sorry, minus something which is linked to entropy production. And writing this entropy production, the different parts of the cycle, in terms of the Kullback divergence, we get this lag. And the minimum value for this lag is exactly the gap between Otto and Carnot. So looking for the, when we do this compression and the expansion protocol, we can look for this divergence, for the divergence between the forward and the backward protocol. And this divergence will give us how irreversible is our engine. And we can measure it performing quantum-state tomography along the time, a stroboscopic quantum-state tomography, and we can characterize the irreversibility in that sense. So if we perform the evolution in a quantum adiabatic way, in the which means that we are performing an evolution without transitions. It's not the adiabatic definition of thermodynamics, and in the sense of the adiabatic theorem. As the final Hamiltonian is different from the initial Hamiltonian, we end up in a state which is an out of equilibrium state. So we can call this part of the entropy production, this part of the divergence as quantum friction, and this part will be a kind of a residual lag. So I will mitigate this quantum friction in few slides in an experiment. Okay, and all the treatments that all the theoretical description of this engine that I showed to you was based in the fact that in the driving part of the protocol, we have a unitary evolution. So we can also test in the lab to see how unitary is the evolution that we really implement. Using the quantum process tomography, we can write a general evolution in quantum mechanics as a map like this. And we can choose a basis of operators to express this map. We choose this basis, which is nice because in this basis, any unital process, any process that preserves the identity, has a unitary, a real map, a real map matrix. And here we have this map matrix for compression and expansion. And the argument of this process matrix is expressed here in color. So we have a real metric, and this is the time that takes to open and compress the gap. And then we can change the time, and we can perform also this process tomography. And then, in the end of the day, we can characterize how far away from a unitary evolution we are in the laboratory. So, for this very short, short evolution, the deviation from a unitary evolution is small. When we go to the limit of an adiabatic evolution, a evolution without transitions, so this is the transition probability between the ground to the excited state. When we go in the direction of the adiabatic evolution, we get a bigger deviation from a unitary evolution. It's not only due to the coherence, because we are here in microseconds, so we are order of magnitudes in this dynamics. The dynamics is order of magnitude smaller than the decoherence time. But here we have some imperfections of the driving field, the field that we modulate. So as we let this field switched on for a long time, we have a bigger deviation from the unitary evolution. So this is also an argument to, if you want to perform something in a thermodynamic cycle in the lab, we have also to have it in mind. So performing adiabatic evolutions in the unitary evolution, it's not easy to do. So, and these are the transitions probability that in function of the time that we that we use for the expansion and the compression protocol. Okay, we can also write a fluctuation theorem for a cycle, for the Carnot cycle, the Otto cycle, sorry, for example. This is the integral one, this is this is the detailed one, this is the integral one, and use the Jensen's inequality, we obtain the limit, which is exactly the Carnot limit, and then we can define efficiency with this kind of theorem. We can also think about other definitions of efficiency for a quantum system, but in this case, we consider this definition. And in order to compute that, guys, we need the marginal distributions for work and heat. So in the case of an engine with a full thermalization, we can compute the characteristic function of the whole protocol, and we can split it in compression and expansion in this way. And measuring this characteristic function, we can get the work distribution of the engine. So this is the work distribution of the engine for different times. Here we have the extracted work is negative, so the engine does not work as an engine because we are performing the cycle so fast. And in this case, the engine starts to work as an engine. Each of these peaks are associated to a different history of these transitions between the ground and the excited states. And these are the energies associated to each of these transitions. So I have 16 possible paths, but I just have 9 peaks because some of them are degenerated. Okay, and I can also use the crude relation in order to measure directly from the experimental data the variation of free energy. And I have all the information about interproduction and so on. And this is the heat distribution measured in that experiment. And that algorithm that I showed to you, if we characterize this algorithm using quantum process tomography, we can see that we are implementing a thermal operation because we are performing this algorithm in a given of a time window. So in the end of the day, for the working substance, it is thermalization, right? Okay, we can arrive at complete thermalization in 7 microseconds in this setup. So we prepared some different conditions for the hot medium, and then we measure the average work, the average heat, and so on. And we characterize the power and of this engine. So if you compress and expand the gap very fast, it's not possible to extract work. We have to inject work, and we just produce entropy. But at some point, this start to work as an engine. At maximum power, in this implementation, we was able to get an efficiency about 42%. And the maximum auto-efficiency for the configuration of the gaps that we considered was 44%. So we could go very close to the auto limits. When we look for the efficiency in terms of this time for the gap compression and gap expansion, we see that this is completely compatible with the lag. This is the efficiency lag. This is the sum of these two Kullback divergence. So these are the entropy production in the two parts of the cycle, between and before the thermalization of the hot reservoir. And it's completely, okay, we already know from the theory, but it should be, right? It's completely compatible with this efficiency that we measure in the lab. So all the irreversibility is associated to this lag. So we would like to fight against this lag. One way to do it is to use this idea of shortcuts of adiabaticity. It was introduced by Michael Berry, and there is this very nice paper by Mauro, John, and Adolfo Del Campo suggesting to use it in order to increase the efficiency of an engine. So the idea is to add a term in the Hamiltonian, which is this super adiabatic term that can be computed in this way. In our case, as we are working in a kind of a rotating frame, I didn't mention it, but I can say more about the technical details later. It's just to do a kind of offset, an off resonant field when we drive the system to compress the gap and to expand the gap. So, and in this case, we have this kind of effective Hamiltonian, and then we can perform the rolled thermodynamic cycle without production. So these are the working distribution for these different kind of engines, the engines that I commented, with different times for the compression and expansion, using the conventional driving. And then here we are using this super adiabatic driving. So we can erase some peaks in the work distribution that does not depend, these are the time for compression and expansion. So the work distribution does not depend much on the time for the operation due to this super adiabatic driving. And then in this case, we have a very good efficiency for short time. So we can go very close to the auto limits. And then we have increasing the power, which is quite considerable. So we can make the engine work in this region where the engine should not work. But okay, we still have this residual lag. And another thing, these are the efficiency lag that we have when we do this driving. And we can also write it in terms of the auto limit. So, and in this case, the key state to define this relative entropy is the adiabatic state, the state that we obtain after an adiabatic evolution. But we can do more. I will talk about this in 2 minutes, right? So we perform the same cycle now, but now using an incomplete thermalization. So when we do this finite time driving, we will produce some coherence, and this coherence is an extra source of entropy production. But here we will not thermalize completely the system. So we have some coherence that was produced here being transferred to this other part of the cycle. In this experiment, we are using this 4-qubit molecule, where we have 4 carbons, and each one plays a different role. We again have the radio frequency field playing the role of the reservoir, but we encode the state of the reservoir in some qubits, and then we transfer the heat in a suitable point of the evolution. So again, as also Gabriel commented, we can write this lag in terms of, so this is the lag for the thermodynamic cycle, for the Otto cycle, with incomplete thermalization. So there are one more term here. And then we can split the lag in terms of diagonal and non-diagonal parts. But as we have a cycle, the energy basis changes along the cycle. So we have here some key states that depends on the part of the cycle that you are. So this is the theoretical paper where everything is explained. The experimental results that I will show was not published yet. So here we can see that in the coherent contribution for this lag of the efficiency, we have different signals. And then depending how we deal with the parameters, we can get some kind of dynamical interference. And then we can improve the efficiency of the engine using this kind of interference. And then we can compare an engine with and without coherence, switch on and off at the phasing here. So I will jump to the results. And here I have a fixed thermalization time, and here I fix this compression and expansion time. And here we are comparing an engine that has coherence and the engine with this dephasing. And then we can see a kind of enhancement due to this interference that we have along the dynamics. But when we have an engine with coherence, so this is the power, and also considering these two ways to control the parameters, and this is the freezing mode. So the green curves and points are the coherent operation of the fridge, and this is the dephased operation of the fridge. So in the freeze mode, we can get an even better improvement using coherence. So in the end of the day, the main point about this is when we have a quantum engine, we have to consider that we have coherence, so the adjustment of the parameters in the operating the engine should be considering that we have coherence. So we can go in a situation where we have an improvement of the efficiency of the engine, for example, or the power, or we can go to a situation where we have a decrease of this of the power, for example. So these are some of the results that I commented here are in these papers on arXiv, and some of them will appear soon on arXiv. And this is a picture of São Paulo at night. So that's why we are really concerned about entropy production. And if you want to visit us, you will be more than welcome. Thank you.
Questions?
Thanks for a very nice talk, Roberto. Just a question regarding the sort of possible cost of implementing that shortcut